Imagine a future where the world's cheapest clean hydrogen doesn't come from massive solar farms, wind fleets, or high-tech electrolyzers, but from something far simpler and far more abundant: heat. Not electricity, not expensive renewable power, but heat itself. Heat from concentrated solar plants, deep geothermal systems, industrial waste heat, or even heat produced by nuclear reactors and small modular reactors. That's the bold idea behind NewHydrogen, a small but ambitious company developing an early-stage technology called ThermoLoop. And if the company is right about its potential, this heat-driven hydrogen process could reshape how we think about green hydrogen economics, scale, and the future of clean fuel production. Today, we break down what NewHydrogen is actually building, why ThermoLoop is drawing attention across the hydrogen and SMR sectors, what the company has achieved so far, and what remains unproven as it attempts to move from laboratory success to real-world commercial systems. To understand why ThermoLoop matters, we need to revisit hydrogen production. Right now, most hydrogen worldwide is made using a mature method called steam methane reforming. It's cheap, but it comes with a heavy carbon cost because it uses natural gas and produces large quantities of CO2. Some facilities bolt on carbon capture units to reduce those emissions, but that simply turns gray hydrogen into blue hydrogen, which still depends on fossil fuels and permanent carbon storage. On the clean side, green hydrogen production relies on electrolysis powered by renewable electricity. This is cleaner, but it is also expensive. In fact, electricity alone can account for more than 2/3 of the cost of producing a kilogram of green hydrogen, especially in markets with high power prices. This electricity cost problem has slowed down many green hydrogen projects and has left investors searching for alternative pathways. NewHydrogen proposes a different route entirely. Instead of using electricity as the main energy input to split water, ThermoLoop uses heat. The system is based on thermochemical water splitting cycles where water molecules are separated into hydrogen and oxygen through high-temperature chemical reactions. These reactions use solid materials that change their state when heated and exposed to water vapor. During the high-temperature step, hydrogen is released. Then, in a second step, heat regenerates the materials and resets them to their original state. The materials loop back and forth, driving a continuous cycle. Water goes in, hydrogen and oxygen come out, and the only real energy input is heat. If the system can run efficiently and the materials can last through thousands of cycles, hydrogen production could be significantly cheaper than conventional green hydrogen, especially in areas with abundant heat. The company's big breakthrough came in mid-2025 when it announced its first laboratory production of hydrogen using a ThermoLoop bench-scale unit. While this is not a commercial demonstration, it represents a crucial milestone, proof that the thermochemical cycle works outside of theoretical modeling. NewHydrogen has also been working closely with researchers at the University of California, Santa Barbara, and later that same year, it filed a second provisional patent covering additional aspects of its technology. These steps show both technical progress and a growing desire to protect intellectual property as the company moves from basic research into pathway development. ThermoLoop's potential becomes even more interesting when paired with heat sources that already exist. Industrial facilities often waste enormous amounts of high-temperature heat. Geothermal plants can deliver stable heat flows. Concentrated solar plants generate temperatures far beyond what photovoltaics can achieve. And perhaps most notably, nuclear plants, especially small modular reactors, produce massive quantities of steady, high-quality heat around the clock. NewHydrogen suggests that coupling ThermoLoop with an SMR could create a new type of highly reliable hydrogen production hub. Instead of converting all of a reactor's heat into electricity, developers could divert part of that thermal energy into a ThermoLoop system. Under this scenario, a single 50-megawatt SMR could theoretically support production on the order of tens of tons of hydrogen per day, depending on configuration and process efficiency. This could give SMR operators multiple revenue streams: electricity, hydrogen production, and potentially even clean water if desalination is added. But the SMR connection is also strategic from a cost perspective. Nuclear facilities have extremely high capacity factors. They rarely shut down. Electrolyzers paired with solar and wind farms only operate when the sun shines or the wind blows, reducing their utilization and increasing their cost per kilogram of hydrogen. Heat-driven hydrogen production, on the other hand, can operate continuously alongside an SMR. This creates a more stable cost profile and potentially makes hydrogen pricing more predictable for industrial buyers. It also aligns well with long-term decarbonization goals in sectors like ammonia production, steelmaking, and long-distance transport. However, while the concept is promising, it's still early. NewHydrogen's ThermoLoop remains at laboratory scale, and there is no commercial plant yet. Many early-stage cleantech companies have struggled to scale from controlled laboratory environments to real-world industrial settings where equipment needs to run for years under extreme conditions. For ThermoLoop to succeed, the materials inside the reactor must withstand thousands of cycles without degradation. The reactors must maintain thermal stability. The capital cost must be competitive with both electrolyzers and fossil-based hydrogen units. And regulators must approve a completely new class of chemical thermal equipment that will operate at high temperatures and interface with major industrial heat sources. These hurdles are not trivial. There are also market challenges. Even as governments push for clean hydrogen, demand is still forming. Offtake agreements, hydrogen transport networks, and policy incentives vary by region. Competing technologies, such as solid oxide electrolysis paired with nuclear heat, are also advancing and attracting attention from major players. NewHydrogen must therefore demonstrate not only technical novelty, but economic superiority. Still, the idea of producing hydrogen from heat instead of electricity remains compelling. If heat sources are cheap, stranded, or underused, like geothermal wells, industrial waste heat, or SMR thermal output, then heat-driven hydrogen could carve out a strong niche. It could also fit into hybrid energy parks where hydrogen provides storage, industrial feedstock, and fuel for transportation. In these integrated systems, ThermoLoop could reduce the pressure on electrical infrastructure, allowing developers to tap into heat resources that electricity-focused approaches often overlook. For hydrogen developers, consultants, and investors, the ThermoLoop story is a reminder that cost reduction in hydrogen can come from unexpected angles. It's not just about chasing cheaper electricity, it's about rethinking where the energy input comes from. Whether ThermoLoop becomes a breakthrough or remains a niche technology will depend on how well it scales, how its cost curve evolves, and how effectively it pairs with SMRs and other high heat sources. If you want detailed help evaluating hydrogen technologies, building financial models, or comparing hydrogen production pathways, you can find expert tools, templates, and training at reneenergy.com, designed to help you master green hydrogen project development and financing.